We're going to talk about the law of gravity as discovered by Sir Isaac Newton. Now, when we say a law in science, this is a description of how nature behaves. It is not a law as in man has decided this is the way it's going to be. Scientists have uncovered this is how nature operates. The law of gravity is actually a mathematical equation, and this is that mathematical equation. So do not panic. This is not a high-level math class here, but if you understand at least what this says, it's going to be a lot more understandable when we start using these concepts later. F is the force of gravity. G is a constant, kind of similar to Kepler's constant, but this G actually works for all objects. The force of gravity always involves two separate masses, and R, like radius, is the distance between the centers, like the center of the sun and the center of the Earth. Now, what does this law of gravity mean for you and I? First thing is, it says that every object that has mass has a force of gravity. That means that there is a force of gravity where the Earth is pulling on the moon, but the moon is also pulling on the Earth. And of course, this is what gives us things like tides. Every two objects in the universe has a gravitational attraction to each other. If you drop a stone to the Earth pulls down on the stone, but the other half of this that most people don't recognize is the stone is actually also pulling up on the Earth. The Earth is so big, so massive, it has so much inertia, it's not going to accelerate upward. The stone is so small that we can see the stone falling. But every grain of dust, every star, every planet gravitationally tugs on every other. If you've got something that is small and cute, like a puppy, it's going to have a much smaller force of gravity than something large like the Earth, or something really big like the sun, or something really, really, really big like a black hole. So there is a direct relationship between size and amount of gravity. Big things, a lot of gravity. Small things, little gravity. One of the other things that Newton's law of gravity explains is, excuse me, it is an inverse squared law. Now, what does that mean? It means that, let's say you are standing on the surface of the Earth, and the force of gravity on you is one force. Okay, you weigh, let's say, 100 pounds, and that's just a pretend number. And you are one distance from the center of the Earth. If I could put you magically in a spacecraft and take you so you are 2 radii, or twice as far away, the force of gravity on you would not be half. The force of gravity on you would be 1/2 squared. So inverse, meaning the bottom of a fraction, the inverse gets squared. So if you double the distance, the force on you would be 1/4, and you would only weigh 25 pounds. If I could take you, put you on another spacecraft and get you to a point where you are 3 radii away from the Earth, the force of gravity on you would be 1/3, the inverse, squared, or 1/9 of your total weight, and at that distance you would only weigh about 11 pounds. So aside from the numbers, what does this mean? It means that force of gravity gets weaker really, really quickly with an increase of distance. If you get just a little bit further away, gravity goes from being very, very strong to much weaker very, very quickly as you get further and further away. This curve that we've drawn here gives us kind of an idea of how gravity operates. If you are at one radius or on the surface of a planet, the force of gravity is really, really big. Double the distance, it goes down to 1/4. Three times the distance, 1/9. 4 times the distance, 1/16. 5 times 1/25, etc. So it means that gravity gets weak very, very quickly. The other thing it says is this. If those of you who've had some math, this curve approaches but never actually reaches zero. That means that no matter how far away you get, even out to the orbits of Pluto and Neptune that are a long way away from the sun, the force of gravity exerted by the sun is very, very small, but it's still there. And so there are gravitational attractions throughout the cosmos that are billions and billions of light years away, and they are still one object pulling and pushing on another. This is not so much the law of gravity, but let's review a little bit Newton's first law, or law of inertia. Newton's first law, or law of inertia, says an object in motion tends to remain in motion. And this poor fella riding his motorcycle, the motorcycle stopped quick when it hit the tires, and he came off, and he is an object in motion, and he's going to keep moving until he hits something, which unfortunately looks like the ground. This applies to straight line motion, but it also applies to things that rotate. Circular motion. If you get a top spinning, and once it's spinning, it wants to keep spinning. Bicycles are the same way. You get a bicycle wheel spinning, and they're going to keep spinning for a long, long distance until they move so slowly that the bike falls over. Why do we care about this in astronomy? Well, we care about this because everything in astronomy spins. Planets spin, the solar system spins, the sun spins. And how do you explain that everything out in space, the Milky Way galaxy spins? How do you explain that everything spins? It is leftover motion from the beginning of the solar system or the galaxy. And it is called the conservation of angular inertia. Angular means spinning in a circle. And a spinning object is going to want to keep spinning. Couple examples aside from this, the top example we used. One is a football when it is spiraled. When a quarterback throws a football, they don't just let it go through the air. It has a spiral on it so that the spinning football is actually going to be a lot more stable than the non-spinning football. Your bicycle, if you just try and stand it up, it's going to go boop and it's going to flop right over. But if the wheels are spinning, it is very stable in that orientation and it's going to want to keep spinning. And we see the same thing with planets and solar systems and the sun. They have been spinning for billions of years and they're going to keep on spinning. And they are quite stable in their orbits because of this concept called angular inertia. All of the planets that are spinning around the sun, we think they get their original angular momentum or angular inertia because of the original motion that was possessed by the early solar system. The plane of disk that made up our entire solar system was spinning in one direction, and that leftover angular motion is what gives us all the spin and orbit, all the orbits we see today. Now, when the early solar system was created and started spinning, it was spinning kind of like if you have a little dress, and some of you have done this and some of you haven't, but if you have a dress that's kind of long and flowy, and if you spin it really quickly, instead of lying flat like this, with a lot of speed, it has a tendency to move outward and flatten. The same sort of thing happens if you have a lump of pizza dough. If you go to a pizzeria and they kind of flatten it a little bit and start spinning it, they have this big flat plate looking shape of pizza. Everything that spins has a tendency to flatten out like this. And the ball of gas that made up the early solar system, with the spin left over from its original creation, created what is called the plane of the ecliptic. And that plane of the ecliptic we've talked about many, many times, where all of the planets are lying on the plane of the ecliptic, or pretty darn close to it, except for our dear friend Pluto. Pluto has an angle of about over 17 degrees from the plane of the ecliptic. So the sun and all the other planets are really, really close to being on this flat plane. And there's poor crazy Pluto at about a 17-degree angle. And that's one of the many reasons we'll talk about in the future why Pluto we don't think was one of the originals. It was an add-on feature. This leftover rotation, this leftover inertia from the beginning of the solar system explains a whole bunch of different phenomenon that we see. Let's talk about ice skaters. And I'm sure somewhere in your history you have seen some of these ice skaters. If you see an ice skater and she or he begins to spin and their arms are way out, they're going to spin relatively slowly. When they pull their body close together, the spinning rate of speed, they go faster and faster and faster. This is due to something which is called conservation of angular momentum. So if you've got an object that has a big radius, it's going to rotate kind of slow. If you just make the radius smaller, the rotational speed goes up. And this also explains a lot of the rotation we're going to see in our own solar system. The sun has an axis that it orbits around. The sun orbits its own axis once about every 30 days. Leftover momentum from the beginning of the solar system, then way out on the outer reaches, you've got Neptune, and Neptune has got an orbit of rotation that's over 180 years. So the closer to the center, the faster something's going to rotate. Here are some examples of this. Mercury, 88 days, and there's our Neptune. Oops, I pulled that out of my memory and I pulled it out wrong. Neptune, 165 days. So things that are close to the center orbit fast. Things that are far away orbit more slowly. And we'll see this in lots of different examples. That, ladies and gentlemen, ends the last topic, and we will see you next time.